So looking at the integration technique, integration by parts, again, let's recall a differentiation rule, in this case, the product rule. So if I'm going to differentiate the product of u of x and v of x with respect to x, the product rule says we get u prime of x times v of x plus u of x times v prime of x. So one thing I'm going to do here is use this, first of all, to reorder. In particular, if we're starting with this equation, one thing we can do is isolate u of x times v prime of x. U of x times v prime of x must be equal to the derivative of u of x times v of x minus u prime of x v of x. So all I did there is just subtract u prime v to the left-hand side. And of course, I've kind of swapped left and right-hand side because I do want to focus on the left-hand side. So reordering the product rule, we get this. Then what we can do is take the integral of both sides of this expression. And that tells us that the integral of u times v prime should equal the integral of the right-hand side. I am going to split that up into the difference of two integrals using my integration properties. So we get the integral of the derivative of u times v minus the integral of u prime times v. Now, when I have this here, again, there's three integrals. The one that really is something we can write in a more simple manner is this middle one here. We have the antiderivative of the derivative of something. So when I'm rewriting this equation, I'm going to rewrite the first and the third integrals as they are, but this middle one, I'm going to recognize I can write that as just u of x times v of x. So what we get here is this formula. Now, looking at this looks very complicated and it's not immediately clear how we can apply this, but that's part of what we're going to work on. One thing I'll say is that much like I've talked about with u substitution, these are all functions of x, but a lot of times, especially to help us remember the formula, we kind of drop that of x notation and we think of things, so we think of this as just u, and then we lump this together as dv. And likewise, this is v, and we lump this together as du. So kind of the shorthand way of writing this, but also, like I said, that might make it easier to remember, is that we're saying the integral of u dv is equal to u times v minus the integral of v du. So I'll box that in pink here. This is equivalent to the box part above. It's just a little bit easier to remember. We don't have to say all those of x's. So what does this give us? What you want to think about is that the goal is that we're going to try to integrate something, and we want to interpret it like what I have on the left, as the product of a function u and the derivative of a function v. This formula allows us to unravel it to equal what we have on the right. So looking at this, the main thing we can see is that this is only going to be helpful if the integral of u prime v is somehow simpler than the integral of u v prime. Because, again, we're trying to get to the point where we get rid of all the integrals. And so we're going to see in examples that when we use this successfully, that's exactly what happens. So the main task here is, once you've determined that you want to try integration by parts, well, you have to view the integrand in some way as a product, and you have to be able to identify one of the things in that product as u and one of the things as the derivative of v. So again, the more practice we get with that, the better. In this particular video, I want to just look at one kind of starter example and also address that idea of having to decide which one's u and which one's v prime. So what I have here is a product, x times e to the x. So it seems natural that I might consider trying to use integration by parts, where we looked at having an integral that you're starting with where you have a product in there. So what I have to decide is which of my things in my product is going to play the role of u, and which one's going to play the role of dv. So there's two natural kind of assumptions. So let's first let u equal x and dv the other part. So organization-wise, I think it's really helpful to get into a habit of identifying what these are and kind of structuring this. I like to write u and dv on the first line. So notice that what I'm doing is I'm taking what I'm integrating here and I'm splitting it up into these two pieces. Once I define u and I define dv, I should be able to figure out what du is and what v is. So if u is x, then du is just dx. And here we want to find the antiderivative of e to the x dx, and that's just going to be e to the x. So when I'm now trying to rewrite this integral, so I start with what I've thought of. Let me write this a little bit more space. So I'm starting with this, and I've interpreted this as u times dv. And remember what we have in the pink box. What we say this is equal to is u times v minus the integral of v du. Now you can use the kind of structure here. So we're going to take u times v. So you always multiply along that diagonal. And we're going to subtract the integral of v du. So down on the bottom here. And so if I set up my structure like this, I can kind of remember that visual as well. Notice that in the right-hand side, so the new part, we never use dv. dv was present in the original integral, but we actually don't use it in what we're setting it equivalent to. So one of the things I noted in the previous page is that we hope that the integral that we've introduced on the right-hand side is simpler than the one we started with. And arguably, I can say that that's true here because I know how to antidifferentiate e to the x. The problem was I didn't know how to antidifferentiate x times e to the x. So in terms of solving this, now we see, so we have this x e to the x, that's going to be part of our antiderivative. And now I'm going to subtract the antiderivative of e to the x, which is e to the x. This is an indefinite integral, so we'd have a plus c here. And here's my final answer. Again, if you were to differentiate what I have in the box there, you can verify that you do in fact end up with x e to the x, our original integrand. Now, what if we had swapped u and dv? So this choice that we made worked out nicely, but was that arbitrary? What if somebody had chosen to break the product up differently? Well, it turns out it wouldn't help us out, but I want to show how you can kind of recognize that. I think a lot of times there's this pressure that you have to know what the best choice is, but when you're getting used to these examples, you can try things and then backtrack if they kind of indicate that maybe that choice wasn't great. So to be clear, what I have above this dotted line is a complete answer and correct solution to that above. So this is just kind of an exploration. If I were to let u equal e to the x and let dv equal x dx, that's another way of breaking up the product that we started with. A perfectly reasonable way. Here, du would be e to the x dx, and v would be x squared over 2. So with that, from the page above, we would be able to rewrite the original integral as, again, u times v, which in this case is e to the x times x squared all over 2, minus the integral of v du, which would be x squared over 2 e to the x dx in the integral. So this is, again, according to what we have above, this is a completely correct statement I have here. So there's nothing wrong with that. The problem is that in some sense you could argue that the integral we have on the right-hand side is more complicated than the one we started with. The problem here was I had this x, and we liked that in the example above, the x went away. We just had e to the x. But instead of going from x down to a constant, I went to a higher power of x. So that's almost even more complicated. And the problem is, I don't know the integral of this. So while this is a true equation, it doesn't help me solve the original integral. So that would be, for me, an indication that maybe I should go back and check my choices there. So when you're practicing these and you find yourself in such a situation, that's a good indicator that you could maybe go back and try something else. You're not always necessarily going to find the right assignment right away, and that's okay. The more practice you have with this, the better intuition you'll get with making such an assignment. And there are some general rules. I know some people have kind of schematics for that, but just very broadly, what I want to point out is the following. So when you're using integration by parts, you want to choose u and dv so that, first of all, we would like, if possible, for u prime to be simpler than u. So that is kind of what's happening here. Let's go back up here and look at this. We went from u being x to u prime being 1. So that certainly is kind of simpler in that direction. In this case, the derivative was the same thing as u. So we didn't really gain any traction from that. And this first rule we're looking at here is really the one I was talking about that affects whether or not that integral we end up with on the right-hand side is simpler than the one we started with. The second general rule, which really didn't come into play in this example, is that we want to choose dv so that it's possible to anti-differentiate. So in this case, choosing dv to be e to the x or being x, that wasn't a problem. I won't go into it now, but an example that we're going to look at in class is the example of the integral of natural log of x. And in this case, there's two things going on. First of all, you might be thinking that's not a product. Well, I can write it as a product of 1 and itself. But the other thing is that choosing ln of x to be dv would be problematic, because then to find v, you'd have to find the antiderivative of ln of x, which is the question we're trying to solve here. So with the second thing here, we're seeing that I'd be forced in that case to choose ln of x to be u, and then just 1 dx to be dv. So these two things are generally kind of good guides for how to choose that. And then the last thing I want to address, just because we talked about it with u substitution, is the idea of a definite integral. So there's not too much of an issue once I throw bounds on the integral. So if I have the same thing we looked at, so we already know the integration by parts technique, what do we do if we have bounds here? We don't have to deal with the problem of introducing a new variable like we did with u substitution, right? When we did this correctly up here, everything was still in terms of x. I would say the problem I sometimes observe is somebody might forget to evaluate the bounds on this part. So you should end up, if it's a definite integral, you should end up with a numerical answer. So sometimes I'll see people only evaluate the bounds on the integral they introduce on the right-hand side. So the way I would interpret this here, again, using the integration by parts we already did, I would get that the antiderivative we said was this. We said we could rewrite it in that way. Now, not only do I then supply the bounds 0 to 1 on the integral, you also want to put them on this middle part here. Now, some people like to, in this stage, quickly evaluate this, plug in 1 and subtract 0. That's fine. I also, the other way you could do it, which I kind of prefer, is to first deal with that integral. So x e to the x, the antiderivative of e to the x is e to the x. And then just recognize that you have to deal with those bounds on the whole thing on the right-hand side, not just on e to the x. And then we would get 1 times e to the 1 minus e to the 1 minus 0 minus e to the 0. And in fact, this cancels. We have 0 here. We just end up with e to the 0, which is 1. So not as much of a warning there with definite integrals, but again, like I said, the most common mistake I might see is somebody forgetting to evaluate the middle part there.